Dear students, welcome back to my lesson. I'm Mr. Idris, physics teacher at Paris Private School. I'm super excited to see you again with a new chapter. And after we finish chapter 1, I got many requests from the students to explain the other chapters and the entire chapters of physics for grade 12 students. On today's lesson, we're going to start a new chapter, chapter 2, about the rotation, equilibrium, and dynamics. Okay, so just for information, in this chapter we have 3 sections. Okay, section 1 is about torque, and we have 2 topics: the magnitude of the torque and the sign of torque. Okay, so in section 2 we're going to explain about the rotation and inertia. Okay, the center of mass, moment of inertia, and rotational equilibrium. In section 3 we're going to explain the rotational dynamics, such as Newton's second law of rotation, or angular momentum, and rotational kinetic energy. Okay, let's get started. In section 1, chapter 2, section 1, rotational equilibrium. If you remember, in chapter 1, you have learned about the rotational motion and circular motion of an object. So in that case, we treated with the object as a point mass, not rotation. Okay, but in this chapter, you will be able to learn about the rotational motion of an object. Okay, which depends on the shape and the size of the object. Okay, in the earlier chapter, the motion of an object is center of mass, as I mentioned before. Okay, was described by assuming the object was a point mass, which means that the object has only linear or circular motion. Okay, so it is very important for the students to recognize the types of the object. We have 2 types of the object. Sometimes the object can be treated as a point mass. Sometimes the object can be treated as an extended object. So it is very important, and it has been brought in Wizari exam many times. Okay, so when does the object consider it to be a point mass, or when does an object consider it to be an extended object? For the point mass, the object treated as a point mass or considered to be a point mass if it has only translational motion. Okay, when does the object can be treated as a point mass? When the object has only translational motion. For example, when you drop a ball, look, when you drop a ball, in that case, the ball has only translational motion. Why? Because the ball doesn't rotating. Okay, dropping the ball, it means that the object is moving downward because of the gravity without rotating. In that case, the type of the motion of this object is a point mass. Okay, or when the whole car is moving on the flat road, in that case, the types of the car is translational motion. So it means that the car has a point mass, or is treated as a point mass. Okay, or when you throw a ball, also in that case the object has a point mass, or considered to be a point mass. Okay, so it means that the point mass of an object always when the object is moving with a translational motion, not rotation. Okay, so what about the second type? The second type of the object is extended object. When does an object treated as extended object? If the object is rolling or rotating. Okay, for every rotational object, the object treated as an extended object. So take a look at this example. This is an incline. Okay. For example, if you put an ice cube on this incline, okay, because of the gravity, the ice cube will moving downward without the rotation. Do we have rotation? No. The ice cube doesn't rotate. Why? Because of its shape. So in that case, this object has only translational motion. This object has what? Has only translational motion. So this object is point mass or extended object. This is absolutely point mass. Why? Why this is a point mass? Because it has only translational motion. Okay, but in the case, for example, if a bowling ball, if you release a bowling ball here, okay, so in that case, the bowling ball is rolling with the rotational motion or translational motion? Both. Be careful, please. Pay close attention. In that case, When the bowling ball is rotating, it has rotational motion. Okay? So when the ball changes its position, it has translational motion. So finally, we can see when the bowling ball is rolling from an incline, this bowling ball has both types of translation, has both types of motion, translational equilibrium and rotational equilibrium. So in that case, if we have both translation and rotational equilibrium, this object treated as a point mass or extended object, this object treated as a extended object, be careful. Extended object, okay? Or another case, or another example. For example, a ceiling fan. When the ceiling fan is rotating, the ceiling fan is a point mass or extended object because it is rotating, so it is an extended object. Okay, so finally we can say extended object. When does an object becomes extended object? If the object is rotating at itself or rolling and rotating with the changing position. Okay, or when does an object considered or treated as a point mass? If the object has only translational motion without rotation. Okay, look, the types of motion as you learned in chapter 1. Translational motion and rotational motion. In translational motion, we have linear motion or circular motion. Okay. We have some notes about the point mass and the extended object. An object can have both types of motion. It's possible for an object to have both types of motion, translation and rotation, yes, of course, such as rolling a bowling ball from an incline. Okay. If the force is applied on an extended object, the object produces torque. Okay. So we will study in detail in the next lesson, inshallah. Okay. But in the absence of friction, the object will not rotate in an inclined surface, and the object is skidding and it has no rotational motion, and also the torque will not produce. The object can be described as a point mass. So look at this example. This is very important, please. For example, if we have a smooth surface, what is this? Assume that this is smooth surface. Okay. What do we mean by smooth surface? In a smooth surface, it means that there is no friction. Okay? In the case if there is no friction, so if you release a bowling ball from this incline with a smooth surface, the bowling ball doesn't rotate. Be careful. Does not rotate. Why? Because of the smooth surface. So, if you release a bowling ball from an incline with a smooth surface, the bowling ball's motion is extended object or point mass. Absolutely point mass. Why? Point mass. Because there is no rotation. There is no what? There is no rotation. Why there is no rotation on this incline when we release a bowling ball? Because of the smooth surface. Okay? But when an object is rolling down a ramp in the presence of the friction on a rough surface, the object can be described as an extended object, as I mentioned previous example. Okay, take a look at this definition of the point mass and the extended object. What is the definition of point mass? If the object has only what? Translational motion without rotation. Be careful. It is considered to be a point mass. This model describes the translational motion, linear or circular of motion, object to center of mass. The second definition, extended object. What is extended object? An object that has definite size and shape, such as a bowling ball, ring, disc. Okay, it said when the object has what? Rotational motion. Only rotational motion? No. Maybe has only rotational motion or both rotation and translation, such as rolling a bowling ball in an incline or in a flat surface. So in that case, it's considered as an extended object. Okay? So I hope you get advantage from these two types of the motion, extended and the point masses. So it is very important for the students to recognize when does an object treated as a point mass and when does an object treated as extended object. So we have a question related with this topic. Question I think question 1 in section review, a very good question. Guys, look at this question. So this question has been brought in Wizari exam 3 times. Okay, it is very important. Pay close attention, please. Look at the question. Be with me. Okay. In which of the following situations should the object be treated as a point mass? Look, point mass. And in which should the object be treated as an extended object? Okay, so in which of the following examples the object be treated as a point mass, and in which should be the object treated as an extended object? Take a look. A ball dropped from the roof of the house. A ball dropped from a roof of the house. Because the question says drop, the dropping of the ball, it means that without rotating. The question didn't say rolling down from the roof, okay? The question said dropping. In the case of dropping the ball was moving downward without rotating, okay? So it means that we have only translational motion and treated as a point mass, okay? The second one, a ball rolling toward the goal. Look at the question. A ball rolling toward the goal. What do you mean by a ball rolling toward the goal? Assume that, for example, this is the goal, okay? This is ball. So because the ball is rolling toward the goal, okay? The ball rotating. At the same time, change its position. So in that case, we have both. Change in position from this point to this point, for example. Do we have change position? Yes. So it means that this is translational motion. So do we have rotation? Yes, of course. How did you know that it has rotation? Because it says rolling. Say what? Rolling. Rolling has rotation. Toward the goal has translation. Okay? So if the object has both type, translation and rotation together, in that case, the object treated as an extended object. So the second one, B, it should be extended object. Okay. C, a pinwheel in the wind. So you know that pinwheel, it's rotating at itself. Okay, at its position. Sorry, because it has rotational motion, so it should be treated as an extended object. The second one also extended object. Look at D, the last one. Very important, please. Earth traveling around the sun. We know that Earth has both types of motion, translation and rotation. When does Earth has rotational motion and when does the Earth has translational motion? If the question says traveling or orbiting the sun, we have to treat with the Earth as a translational motion. But when the question says when the Earth rotating around itself, in that case, we describe as the rotational motion of the Earth. Okay? Because the question said traveling or orbiting, okay? This is not rotating. Traveling Earth around the sun, treat it as a point mass. Be careful. But if the question says describes the motion of the rotational or rotating Earth around itself, rotating Earth around itself, extended object or point mass, absolutely extended object. Why? Because it describes the rotational motion. Okay? But when the question says traveling or orbiting around the sun, in that case, the object's motion can be treated as a point mass. Okay? Let's go back to our topic. So the second topic in this section is about the torque. Okay? First of all, I would like to define the torque. What is torque? A quantity that measures the ability of what? The ability of a force to rotate an object around some axis measured in Newton meter. So what is torque? Is the ability of the force to rotating an object. Okay? It is very important. For example, this beam, okay, this rod, if you apply a force, look, if you apply the force, what happened to the beam? It's rotate. Okay, so this point is the axis of rotation, and when we apply force on this rod, the rod tries to rotating. Okay, but in the case when the force is applied from the upper, okay, In that case, the object is rotating clockwise. But from below the road, the object is rotating counterclockwise. Okay? So it means that when any force it goes to rotating an object, the torque is produces. So how can you determine the magnitude of the torque? The magnitude of torque it is simple, is tau, is a Greek letter, which is equal to force, ability of force, okay, d, the distance from the axis of rotation to the applied force, and sine theta. Okay, by using this equation, we can finding the value of the torque. What is the units of the torque? Torque measured in what? Newton meter. Why? Because according to this equation, you can prove the units. Okay, force measured in what? Newton. D measured in what distance? Meter. Okay, so another units. So we can open Newton. Newton, which is equal to what? Kilogram meter per second square. Instead of Newton, write down what? Kilogram meter per second square. Okay, so and what is remain? Meter. Meter times meter, it becomes what? Kilogram meter square per second square. Okay? So if the question says which of the following can be measured for the torque, or the torque can be measured in which of the following units? Newton per meter is right, yes. And kilogram meter square per second square also is right. Be careful. Okay? Just open the Newton, you can get these units. Okay. FD sine theta. Okay. So what does torque depend on? The torque depends on what? The magnitude of the force, which is directly proportional. Okay. And the distance from the applied force to the axis of rotation also directly proportional. And the angle between force and distance. What is this angle? This angle between what? Between force and the distance or the arm of the object. Be careful. This angle is the angle between what? F and D. In the case when the angle is not given between force and the distance, you have to try to change this angle between force and the distance. Be careful. Okay, we have a question about that. Okay. What does torque depends on? Force, lever arm, and the angle between force and the distance. Okay. Now I'm going to talk about the lever arm. What is lever arm? Many students are confused with the lever arm and they do not understand with the lever arm as well. Now I'm going to explain in detail about the lever arm. What is lever arm? Assume that this is a thin rod and this is axis of rotation. What is this? This is axis of rotation. Okay. For example, when a force applied at the end, at this point, okay, what is this? This is force. When the force applied on this rod, the rod tends to rotate clockwise. Okay, why? Because this is axis of rotation. When the force applied like that, what happened to the rod? The rod tried to what? Rotating in the direction of the clockwise. Okay. So what is D? In the equation of when we say D sine theta, where is D in this case? D is the distance between what? Between applied force to the axis of rotation. This is D, be careful. Not the whole rod, be careful, okay? The distance in the equation of torque is what? Is the distance between the applied force and the axis of rotation, okay? So in that case, lever arm is equal to D. Why? Or when does, let's say, when does lever arm is equal to D? When the force applied perpendicular to the distance. Okay, look, the angle between the force and D, force, this is D, okay, and this is force is what? 90 degree. Because lever arm is equal to D sine theta. Replace lever arm is equal to d sine 90. Sine 90, as you know, is equal to 1. So finally, lever arm is equal to what? Is equal to d. When does lever arm is equal to d? If the applied force is perpendicular to the distance of the beam. Okay? What is lever arm? The definition of the lever arm is a perpendicular distance from the axis of rotation. Always perpendicular? Yes, always perpendicular. Is the perpendicular distance from the axis of rotation. Look. Sorry. The definition of lever arm is what? Lever arm, which is equal to d sine theta. The perpendicular distance. Always perpendicular? Yes, always perpendicular. Now I'm going to prove for you how and why the lever arm is always perpendicular to the extension of the force. Perpendicular distance from axis of rotation to in a line drawn along the direction of the force. A line drawn along what? The direction of the force or the extension of the force. Okay? Look at this example. This spanner, as you can see, this is spanner, okay? When a force applied on the spanner tries or tends to what? To rotate. Rotate clockwise direction, okay? So in that case, where is the lever arm? Sorry, the force is upward force, sorry. This is upward force, not downward force, okay? This is upward force, so it means that the spanner is tends to rotating counterclockwise. Okay, so in that case, where is the axis of rotation? This is axis of rotation. Where is force? This is force. So can you extend the force? Yes, of course. The line drawn along the direction of the force. What is this? This is force. You can extend the force, okay, in a straight line as it is direction. Where is axis of rotation? This is axis of rotation. What is this? This is axis of rotation. The line, what is lever arm? Perpendicular distance. Perpendicular distance from where? From axis of rotation. To what? The line drawn along the direction of the force or to the force. Okay? How many lines, according to math basic, how many perpendicular lines can we draw on this line? Only one perpendicular line. How many perpendicular line can you draw from this point to this line? Only we have one perpendicular line, which is equal to this. Look. So, what is the angle between this line and the force? Is what? Perpendicular 90 degree. So, what is this? This is lever arm, which is equal to what? D sine theta. So, sometimes the students ask it, they say, teacher, the lever arm is always perpendicular to the direction of the force? Yes, of course. Okay? Let's go the next page. Okay. Well, what is the SI unit of the torque? And write it's fundamentally Newton per meter, which is equal to kilogram meter square per second square. This is lever arm, okay? A force applied on the extended object can produce a torque. This torque in turn causes the object to rotate. The direction of the lever arm is always perpendicular. Yes, always perpendicular to what? To the direction of the applied force or the extension of the force. Okay, now I'm gonna show you some different types of the lever arm. Okay, for example, this is a thin rod. Okay, this is axis of rotation. What is this? This is axis of rotation, okay? If the force applied like that, this is force. Is this force perpendicular? No, because this force is not perpendicular to the distance, so that is why lever arm is not equal to D, okay? What is this? Distance from the applied force to the axis of rotation is D. Be careful, there is a difference between D and lever arm. This is D. From applied force to the axis of rotation. What is this? This is force, okay? So where is the lever arm? First of all, you have to extend the force. You have to extend what? The force. And now after extending the force, you have to draw the line from the axis of rotation perpendicular to the line drawn in the direction of the force. Okay? How many lines can we draw from this point to the force perpendicularly? Only one line. So which is equal to what? Which is this line. Look, this is perpendicular and this is lever arm. Okay, which is equal to what? D sine theta. Okay, another example. Another example. Okay, this is axis of rotation. Sorry, example should be like that. This is axis of rotation. If the force is applied like that, this is force applied on this point. Where is D? D. In the equation of the torque, as you know, we have F D sine theta. This is the angle between force and D, and this is D. Okay? The distance from applied force to the axis of rotation. So, where is lever arm? So, the lever arm in that case is, at first you have to extend the force. Okay? You have to extend what? The force. Okay? So, how many lines can you draw from the axis of rotation perpendicular to the direction of the force? Only one line. Perpendicular. Okay? This is perpendicular. So, this becomes lever arm. Okay? Where is lever arm? Here. This is lever arm, which is equal to what? D sine theta. Okay? Hope you get understood about the lever arm. Okay? Sometimes the question asks us to find the angle by giving distance and the lever arm, or sometimes the question asks us to find the distance by giving the angle and the lever arm. There is a relation which is equal to what? Lever arm is equal to what? D sine theta. In the case when D is unknown, how can you determine D? By giving lever arm and angle. D is equal to what? Lever arm divided by what? Sine theta. You can find it what? The distance. So how can you find angle? Angle is equal to what? Sine inverse lever arm over what? Over D. In this equation you can finding the angle, this angle, or also you can finding this distance. How can you find this distance? When angle and lever arm is known. How can you determine this angle when the lever arm and distance is known in the question? Let's go to another page about the questions which is related with the torque. Question 1 in chapter review. Look at this question. Explain how an orthodontist uses the torque to straighten or realign the teeth. The orthodontist uses the braces, apply the force at a distance from the base of the teeth. Let's say this is not like the teeth. Assume that this is teeth, okay? So how can you realign or straighten the teeth? So in that case, the orthodontist, they uses the force, okay? This is force applied from a distance. This base is the axis of rotation. To produce more torque, they applied a force farther from the axis of rotation. Okay? So in the case when the teeth is more tilted. Okay? So in that case, the orthodontist, they uses apply forces from a distance from the base of the teeth. The base of the teeth, it means that axis of rotation. Okay, to what? To realign or to straighten the teeth. Look, The orthodontist uses braces applied forces at a distance from the base of the teeth. Base of the teeth, it means that the axis of rotation. Look, this is the braces. This is force applied from a distance. This is distance. Okay? Applied force from what? From a distance to straighten or realign the teeth. Okay. If a force acts on a tilted angle on a rotating object, which means that the angle between the applied force and the arm is not equal to 90, in that case, the perpendicular distance from the axis of rotation to the line drawn along the direction of the force, it becomes what? Lever arm, as I mentioned before. And you have to analyze this force into two components. When does the force can be analyzed into two components? When the force makes an angle with the x-axis or y-axis, as you learned in grade 11, okay, in chapter 2. When the force makes an angle, or when the force is not parallel, not perpendicular, in that case, you have to resolve this force into two components. X-axis with the x component and y component, okay? Which component produces the torque? The component that perpendicular to the distance. This force produces the torque. The others doesn't. Okay. For example, let's show you some examples. For example, if we have a thin rod, this is the axis of rotation. Is this? This is axis of rotation, okay? In that case, when the force is applied like that, okay, this is force, and it makes an angle with the x-axis, for example, 35 degrees, okay? And because this force is not on the x-axis and not on the y-axis, it makes an angle. So in that case, this force can be resolved into two components. Okay, the force can be resolved into two components, or if the force is like that, for example. Okay, this force can be resolved into two components. Why? Because it makes an angle with the x-axis. Okay, this component becomes fx and this component becomes fy. Okay, now how many components do we have? Two components. Okay, fx and fy, because the angle with the distance, okay, so that is why fx is equal to what? F cosine theta. What about fy? F sine theta. So which component of these two forces, which component produces torque? Fy or fx? Absolutely fy. This component has torque. What about fx? The torque of fx is equal to 0 torque. Why 0 torque? Because the angle between the distance and the force fx is 0 angle. Okay, because the angle is 0, or the force, look, fx, the extension of the fx passes through the axis of rotation. So that is why fx cannot produce torque. The torque according to fx is equal to what? Is equal to 0. Why? Because angle 0. Sine 0 is equal to 0. Okay? Now I'm going to show you more case and situations, different situations of the force when applied on the thin rod. Okay? Assume that this is axis of rotation. Visual, okay? This is F1. So this force can rotate this beam? No. Why? Because the force cannot make an angle. So the angle between F and D is equal to what? 0. 0 degree. Torque is equal to what? F1 D1 sine theta 1. Torque is equal to what? F1 D1 sine 0. Sine 0 is equal to what? 0. 0 times F1 D1, 0. Okay? 0 Newton meter. So it means that this force cannot produce torque. Why? Because it is parallel to the distance of the beam. Okay? So in the case when the force makes an angle, F2, okay, this is F2. So this force can cause to rotating this object? Yes, of course. How the beam rotates when F2 is applied on this beam? Clockwise. Sorry, in counterclockwise. This is counterclockwise direction. Okay? According to F2, the second force tends to rotating this beam counterclockwise. Why? Because this force is upward force. Okay? And this beam is rotating around this axis. Okay. Do we have angle? Yes, of course, we have angle. How can we determine torque number 2 is equal to F2 D2 sine theta 2. The torque number 2 is not equal to 0. We have torque. Okay? It is positive or negative? It is positive. Why? Because it's counterclockwise. Because torque can be positive and negative. Now I'm going to explain in detail. Okay? The third force, so what is the difference between these two forces? Only in the angle. Assume that they have the same force. Okay? The third force is what? Perpendicular. Okay? So the angle between the force F3 and the distance is what? 90. Okay? The angle is what? 90 degree. Okay? The angle is 90 degree. F3, the torque number 3, has maximum value. Which one is bigger? Which one produces more torque? F3, F2, F1, F3. If they have the same force, same distance, all forces acted at the same distance. But different in what? Different in angle. So that is why the angle is very important for the torque to be produced. Okay? Zero angle cannot produce torque. More than 0 can produce. 90 degree produce the maximum torque. Do we have a torque bigger than this torque? No. At constant force and D, absolutely. Okay? Another force, which is also parallel, but by 180 degree. So in that case, the force, the extension of the force across the axis of rotation, so that is why F4 also has 0 torque. Why? Why F4 has 0 torque? Because according to this equation is equal to F4 D4 sine theta 4. Torque number 4 is equal to what? F times D times sine. What is the angle? 180. 180 sine 180 is equal to what? 0. So that is why torque number 4 also is 0. How many 0 torques do we have? We have 2 0 torques in that case, in this example. F1 and F4. Why? Because F1 has 0 degree and F4 has 180 degrees. So can we say that torque is equal to 0 in the presence of the force and the distance in these two angles? Yes, of course. 0 degree, 180 degrees. So you can say distance and force are parallel to each other. If the force or the extension of the force is parallel to the distance, in that case, no torque produces. Okay? Another example, for example, the fifth force, if the force applied on the axis of rotation, this is force number 5. Force number 5, the torque, it is torque also equal to 0. Why? Do we have force? Yes. Do we have angle? Yes. Angle is parallel? No. The angle is not parallel. And also we have force, but we don't have distance. Okay, in these 4 examples, we have a distance. Be careful. But when the force applied on the axis of rotation, in that case, D is equal to what? D is equal to 0. When D is equal to 0, Torque is equal to what? Torque is equal to force times distance sine theta. Even we have force and angle, but D is 0. So 0 times force times angle has 0 torque. Okay? So we can say, we can add another one when distance is 0, or you can say when force applied on the axis of rotation. Force applied on the axis of rotation. In that case, no torque produces and torque is equal to 0. Okay? So, maximum positive torque here. Okay? So, when does the object becomes maximum negative torque? If the angle is 270. Look. This is force number 6. Okay? Force number 6. In that case, angle is, what is the angle? Sorry. This is 0, 90, 180, 270. In that case, torque number 6 has maximum negative value. Be careful. When does torque has maximum negative value? If the angle is 270 between force and the distance. Okay? So, when the force makes an angle F number 7 with the angle of 360, also torque is equal to 0. 360 degree, 0 degree, 360 degree, and 180 degree, they have 0 torque. Okay? Okay. I hope you understood this, because it is very important. Okay? So if you have a question, feel free to ask me and leave a comment. Okay? So you can write down your question on the comment. I'm going to explain and respond. Okay? Let's go back to our book. Maximum positive sign of the torque is very important. The torque can be positive and negative. Okay, positive and negative. In the case of counterclockwise, positive. Counterclockwise. As in the case of clockwise, the torque becomes negative. But actually, torque is a vector quantity, but in this book, we will deal with the torque as a scalar quantity. Okay? When does the torque has maximum positive torque? If the angle is 90. When does torque has maximum negative torque? When the angle is 270. Okay? Torque is equal to half of its maximum value if the angle is 30 or 150. It is very important. Okay? So how can you determine this value when the question asks us to find at which angle the torque becomes half of its maximum value? You can find like that. Okay? Because torque is equal to Fd sine theta at constant force and D. Okay, so when does the torque becomes half of its maximum value? We have to finding theta. Theta is equal to what? Sine inverse Fd torque. If force and D are constant, okay. So when does the torque becomes half of its maximum value? Sine inverse of half, or 1.2, 1 over 2. Which angle is equal to sine inverse of 0.5? When theta is 30 or 150. Okay? So you can find for the others, when does the torque becomes 3/4 of its maximum value? You have to find the sine inverse of 3/4. This is 3/4. Which is equal to something, okay? When the torque becomes 1/3 of its maximum value, sine inverse 1/3. When does an object, when does a torque becomes 1/4 of its maximum value? You have to finding the sine inverse 1/4, which is equal to something. So you can check on your calculator for getting this value, okay? So the torque has minimum or zero, theta 0, 180 or 360 degree, okay? So the relation between the lever arm and the torque is directly proportional, okay? Which means that the longer lever arm produces more value of the torque and vice versa, which means that how easily an object rotates depends not only on the how much force is applied, but also on the where the force is applied. So look at the door. Why the handle of the door is located at the edge of the door? Okay, to open the door with by using a small force. In the case when the handle of the door, this is, assume that this is door. Why the handle of the door is located at, this is axis of rotation. This is the hinge, okay? What is this? This is axis of rotation, okay? This is axis of rotation. Why the handle is located farthest from the axis of rotation or at the edge of the angle of to the axis of rotation? To increase what? To increase distance, okay? When the distance increases, what happened to the force? Force decrease at constant torque. Why? Because torque is equal to what? Fd sine theta, okay? Force is equal to Fd sine theta, okay? And F is equal to what? Torque over d sine theta. What is the relation between force and distance? Inversely proportional. More distance require less force. Why the handle of the door located at the edge of the door? To use or require less force, to minimize the force. In the case when the handle is located at the middle of the door, okay, so it means that we decrease the distance to half, okay. D is equal to half of its maximum. D2 is equal to half of D1. Torque number 2 is equal to how many times of force? F2 is equal to how many times F1? Absolutely, it should be twice. Why? Because force is inversely proportional. F1 over F2 is equal to D2 over D1. Come on, replace. F1 over F2, D2, which is equal to what? 1 over 2 D1 over D1. D1 with D1 cancel. What does remain? F1 over F2 is equal to 1 over 2. Cross multiplication. F2 is equal to what? Twice F1. If you decrease the distance of the handle of the door from the edge of the door to the middle of the door, it means that we decrease the distance by factor of 2. Okay? So we change the distance by factor of half, okay? So when the distance changes by factor of half, the force changes by opposite of the half or inversely proportional to the distance, which is equal to twice, okay? The force becomes twice. So we can say when the handle of the door is located at the middle, you require the twice force as before, okay? So that's all for today. Inshallah, in the next lesson, we will continue and we will finish this section. Hope you get benefited and thank you for listening.